Jnanam Paramam Dhyayam. Knowledge is supreme.
In today's lecture, we shall discuss about the uniqueness of primary decomposition. So let us recall what we have done so far. So today we are discussing uniqueness of primary decompositions. So as usual, A is an Archimedean ring. And V is a finite A module. And U is a submodule of V. A is a submodule of V. Then we have proved earlier that there exists an irredundant primary decomposition for U. That means U is intersection of QIs, finitely many, and these QIs is PI primary for I is equal to 1 to R. And irredundant means you cannot drop any one of them. Also we have seen that the associated prime ideals of V mod U is precisely this P1 to PR. These are the prime ideals corresponding to the primary components of U. Moreover, we have also seen that these P1 to PR are uniquely determined. And today we are going to discuss whether the primary components are uniquely determined or not. So question is, which of the primary components is Q1 to QR are uniquely determined? As you will see the answer to this question, not all of them are uniquely determined, but some of them are uniquely determined. So we are going to find out which one. So for this we want to first prove the preparation. We want to prove that the following theorem, which will help us, which is a preparation for answering this question. So theorem, let A, V, U be as above, and U is this primary decomposition, irredundant primary decomposition. This also I will abbreviate by IPD, and let P be a minimal with respect to the inclusion in the associated primes. in the set, this is a finite set of associated prime ideals, and I have chosen P to be the one minimal among them, and it is because it is a finite set, minimal exists, and let Qj, which is appearing here, be P primary. Only one of them has corresponds to this P, therefore I call it Qj, and then I want to look at the map. See, we have a map iota Vp. This is just a notation. This is a map, a localization map from V to V localized at P. V localized at P is by definition S inverse of V, where S is the complement of P. And now you have a submodule U of V, and I localize it here. That one is, and I want to pull it back under this natural map. So iota, let us abbreviate this by iota only. Iota inverse of U localized at P is Qj. That is the assertion. Once I prove this, because this side is uniquely determined by U and P, therefore this side is uniquely determined. So that will prove that Qj is uniquely determined. So in particular, let us record the statement. In particular, primary components of U corresponding to the minimal primes in the associated prime ideals are uniquely determined. And the prime ideal, the primary components corresponding to the non-minimal prime ideals, they need not be uniquely determined. I will leave this to find the example such kind to the participants, but let us prove this theorem first, and then we will digress a little bit on the for the ideals and about the Zariski topology. So proof is very easy. So proof, let us put Q equal to Qj and assume, we may assume that U is 0 by passing to the replace V by U, and let us put so we want to prove, therefore, so with this notation we want to prove that iota inverse of 0 is Q. This is what we want to prove. All right. So we have earlier proved that if I localize at P and look at the associated prime ideals of QP, these are precisely the localizations. So S inverse of Q, where Q belonging to the associated prime ideals of Q, and obviously it should be a proper ideal, so Q should be contained in P. This we have proved earlier. But remember this set, because P is minimal among them, it is clear that this is empty set. This is empty set, since P belonging to associated prime ideals of V is minimal, and Q belonging to the associated prime ideals of Q if and only if Q is one of the pi for some I not equal to j. So therefore from this it follows that because the set of associated prime ideals of the localization QP is empty set, therefore the module QP has to be 0 module only, and hence this means, and so Q is contained in iota inverse of 0. So we wanted to prove equality here, we proved one inclusion. So now to prove the other inclusion, suppose this is not equal, then I can find a bigger submodule. So if W contained in V is a submodule of V with W properly contains in Q with iota inverse iota of W is 0. That means when you push this W to the localization, it becomes 0. Then we should get a contradiction. And how do we get a contradiction? That is because, okay, so then first note that S inverse of W mod Q, this is 0, but this is 0, therefore the associated primes of this should be empty set. But what happens? If you look at the associated prime ideals of W by Q, which is contained in associated prime ideals of V by Q, but Q is P primary, therefore associated prime ideals of V by Q is a singleton P, and this is because Q is not W, we are assuming this is non-empty. Because of this, when I go to the when I localize this P will still survive. So that implies S inverse of W by Q is non-zero, non-empty. But we have just shown earlier that it is empty, therefore a contradiction. So this proves the proposition, and now I just want to remark. So what did we prove? We proved that the associated prime ideals corresponding to the minimal primes, they are uniquely determined. So when you, for example, now let us take a particular case which is very important. So suppose I have a Noetherian ring, A Noetherian, and A is an ideal there, proper ideal. Then we know that A has a primary decomposition, irredundant. So primary components are like this, Q1 to QR, and among them I choose, so we have these associated prime ideals. This is P1 to PR. These are uniquely determined, we know, but Q's may not be uniquely determined. So I choose the minimal one among them. So that means let Q1 to QR, Q1 to QS, some may be minimal among them. So Q1 to QS, definitely there is at least few minimal because it's a finite set. So let these be the primary components of A with respect to the minimal primes P1 to PS in the associated prime ideals of this A by A, which is the set P1 to PS and few more PR. This is IPD. Then we know that these Q's are minimal, Q's are uniquely determined. So therefore, this we have proved that Q1 to Qs are uniquely determined. And now if you look at the corresponding V, recall that V is, this is by definition all those prime ideals which contain P1. So these V1 to VPS, these are precisely irreducible components of spec A by A so they are actually not irreducible, but they are the connected components of this with respect to the Zariski topology. So I have recalled the Zariski topology is given by where the V's are the declared to be the closed sets. We have seen this earlier. So the pictorially what we will look that this, if you, so in particular for A equal to 0, in particular for ideal A equal to 0, then I would like to draw the picture of the spectrum. So if you have a ring A is a Noetherian ring, and we are applying the above result to the ideal 0, A is the 0 ideal, then we have 0 is the intersection of these primary components, and Q1 to Qs are the minimal one, these are minimal, and they are corresponding to the prime ideals P1 to PS, they are minimal in the associated prime ideals of A. Then if you want to see the picture of spectrum of A, these are the V's, they are the connected components, so they don't intersect because the connected components, so like this. But there could be an embedded component, that means non-minimal one will be lying somewhere here or here. So these will be called embedded components. So the components which are not minimal, they are called non-minimal components are called embedded components. That means they are embedded in some other connected component. All right. So now I just want to give one more observation, which will be also very useful in some later lectures, namely this theorem. This is for the rings. So as usual, A Noetherian, A is an ideal in A, and assume that the associated prime ideals of A mod A, they are full of maximal ideals. They are not only prime, by definition they are prime ideals, but we are assuming they are maximal ideal. This is the set of all maximal ideals in A. Then, and suppose A is Q1 to QR, this is the primary decomposition, IPD, irredundant primary decomposition. Then Q1 to QR are uniquely determined. That is because these associated prime ideals are full of maximal ideals. So, therefore, every element there is a minimal element. There can't be any associated prime ideals which contain a maximal ideal, because maximal ideals are maximal with respect to the inclusion. So, therefore, by earlier theorem they are uniquely determined. Moreover, the canonical map canonical homomorphism which one? That is A mod A to, this is the diagonal, I is from 1 to R, A mod Qi. Just map A bar to the corresponding images. These are the corresponding images in mod Qi. This is from I is from 1 to R. This canonical map is an isomorphism. And spectrum of A mod Qi is just a singleton Mi. So proof is, as I have said, uniquely determined follows immediately from the earlier theorem, because all of them are minimal ones. Now I only have to justify this isomorphism, but for that I will use Chinese remainder theorem, because this Qi is Mi primary and Mi's are maximal ideals. Therefore, this Qi will contain a power of Mi, some power Mi power Ri, for some Ri belonging to some natural non-zero natural number. And then because Mi, if I take different I and j, if I not equal to j, then Mi not equal to Mj. So therefore Mi, Mj are co-maximal. Therefore the powers are co-maximal, Mi power Ri and Mi power Rj are co-maximal. Therefore, if I look at this Q1 intersection QR, from here to I have A mod Q1 cross A mod QR, and because they are co-maximal, because these are co-maximal, therefore Qi and Qj are also co-maximal. Therefore, Chinese remainder theorem will tell you this is an isomorphism by Chinese remainder theorem. So that proves the assertion we wanted, and the spectrum is singleton, that is clear. And so that proves minimal primes are isolated, that proves that the primary component corresponding to the minimal primes are uniquely determined, and that is the best we can do. And I would just write for record that so find an example of an ideal contained in A such that A has non-minimal primary components. And they are not unique, and they are different. This is very easy to see, but I want you to construct. So, one possibility is if you take suitable prime ideal and maximal ideal contained in that, the maximal ideal which contain that, and now use this configuration to find an ideal A, so that it has two primary components. One of them is with respect to P, the other is with respect to M, and the M1 is not uniquely determined. So, you have to find two different. So, A you can write it as Q1 intersection Q2, this will be P primary, this will be M primary, and also it is equal to, obviously Q1 is uniquely determined. So, Q1 intersection Q2 prime, this is M primary, this is P primary, and equality holds, but Q2 is not equal to Q2 prime. So, that will show that primary components corresponding to the non-minimal are not uniquely determined. These non-minimal, they are also called embedded, because it is embedded in this, the primary component corresponding to the minimal prime. So, I will just write the name embedded components are not unique in general. All right. So, with this I would stop, and we will continue later. Thank you.